It's late 2019. A man walks down the street when, suddenly, he feels something in the back of his throat. Just a cold, he thinks. As the days go by, his situation slowly declines. A worsening cough, shortness of breath, developing a fever. He decides to go to the doctor.
Your symptoms are unique. I've never seen something like this before. You're the fourth person today to come with these symptoms, but they don't match any known disease or virus. I suspect that this is a new virus. We need to determine if this is going to spread. It could be an epidemic, or even worse, a pandemic.
I can help you, doctor. But first, an epidemic is an unexpected increase in disease cases or the number of people infected in a specific geographical area. An example of this was the Ebola epidemic in West Africa from 2014 to 2016. A pandemic is when a disease's growth is exponential, and its growth rate skyrockets as time goes by, and it affects many countries and geographical areas. A prominent example of this was the Spanish flu in 1918, which infected a third of the world's population and killed millions. The way we model epidemics and pandemics is by using the SIR model. It was developed by William Kermack, a chemist turned mathematician. His partner was Anderson McKendrick, who was a doctor turned mathematician. Together, both Kermack and McKendrick worked together to create the Kermack-McKendrick model, which was an essential piece in the creation of the SIR model.
It's 3 parts. S of T, which stands for susceptibles, I of T, which stands for infected, and R of T, which stands for recovered. At time 0, S of T, or S naught, is the population size that can gain the infection. I of T, or I naught, is the people that are infected at the very start of the virus, and R of T is equal to 0, since there are no recovered. S of T, I of T, and R of T can be depicted by these 3 equations, representing the rate of change for their respective variables. The rate of susceptibles over time is equal to susceptible people S, multiplied by those infected people who came in contact with them, I, multiplied by the transmission rate R, which is how quickly the disease spreads. It's negative since once a susceptible person becomes infected, the number of susceptibles decreases. The rate of infecteds over time is in part proportional to susceptibles, as since R, SI, was subtracted from susceptibles, it's now added to infected. Then, infected people I, multiplied by the recovery rate, are subtracted from the total amount. Finally, the rate of recovered over time is equal to A, the recovery rate, times the number of infected people. For a pandemic, the graph of the SIR model would look like this.
But how can this help us now?
It's using R naught. R naught is how many susceptibles one infected person will infect in the given population. To calculate it, we start with the rate of change of infected individuals. We input at time 0 into the equation. Divide I out, add A to both sides, divide both sides by A, and replace 1 with a variable, R naught. R naught is equal to R, the rate of transmission, times S, the number of susceptible people, divided by A, the rate of recovery.
Now, why is R important? When R is greater than 1, that means there is an epidemic or pandemic. When R is equal to 1, that means there is an endemic, which is a stable virus that continues year-round. And when R is less than 1, that means that there is no epidemic or pandemic.
Therefore, we want to reduce R naught so that it can be equal to or less than 1. This can be done in a few different ways. Regarding R, the transmission factor, we can reduce it by utilizing methods like quarantine, social distancing, travel restrictions, washing hands, and wearing masks. For S, susceptibles, we can reduce it by vaccinating the population. And for A, the recovery rate, we can increase it by developing medicines and treatments that help infected people recover quicker. So, let's go back to the original question. It's 2019 and the doctors suspect a new virus. How can we know if it will be a pandemic?
If we look at the COVID-19 data for Ontario, the starting R naught was around 3, definitely a pandemic. After social distancing, quarantine, and other measures to reduce R naught, the value hovered around 1. Then, we can see a sharp increase around December 2021, which was the advent of the Omicron variant. The answer? Yes, definitely a pandemic.
That's the amazing thing about the SIR model. It relates to the very way we interact and live. During COVID-19 and other epidemics and pandemics, math helped inform physicians and health agencies how to reduce cases through the transmission factor, and when to isolate and quarantine. At the end of the day, we learned that math has the power to turn knowledge into action, and ultimately, save lives.